All right. So this is a YouTube link. I posted it in the chat. So good afternoon, everybody. Welcome to the first class of Physics 110, Introduction to Modern Physics. As I've already told you, these sessions will be live streamed and recorded. So if you choose not to, you can turn your videos off. But I do prefer if you keep your videos on so that we can have human interaction. Now, of course, in these classes, we have lots of people from many different parts of India. Presumably, English is the only common language shared by all of you. But in case you do not understand anything, something I say, if something I say is not clear, then please ask in the chat or please ask in the YouTube live chat window. Also, if you choose to watch the YouTube videos, I request that you go to the live chat window in YouTube and you enter you just type your name so that I know that who is watching, who watched the video. Okay. And as I already discussed with you all, you seem okay with me changing the timing for 3 of our classes from Monday, Wednesday, and Tuesday from 11:15 onwards. And also the second thing is, and the Thursday class will be at 10:30 onwards. And also, as I already mentioned, I would like to have 45-minute classes instead of half an hour long classes. So our classes will go from 11:15 to 12 o'clock. And I hope that will be okay with everybody. And then the Thursday class we'll start at 10:15 and it will go to 11 o'clock. If you have any objections or difficulties with this, you please tell me, okay? All right, now then next you probably don't have a class representative or somebody like that yet. So who wants to be the class representative for my class? Can you please raise your hand if you are interested in being your class representative? Okay, great. We have 1 volunteer, 2 volunteers. Anybody else?
Sir, what is the duty of a class representative?
Who was that? Sorry,
Charan.
Charan. Well, the first duty is to show your face on Zoom. So that means you are disqualified. No, I mean the duty of the class representative is to be the nodal person, be the contact person for me, so that I can communicate with you and you can communicate with everybody else, and also to convey any concerns and issues that students in the class might have to me. Okay.
Okay.
So what I will do is I will set up a poll on Moodle. Okay. Now everybody knows how to use Moodle.
Yes, sir.
Yes, sir.
Great. So
yes, sir.
I will set up a poll on Moodle, and I presume that you all really don't know each other also because you've never had the chance to meet. But for what it's worth, I will put the names of the first 5 people who raised their hands. Let's see, 1, 2. I'm taking the screenshot for that. Abhay, Pranav, Ameya, Charan, and Lavanya. Here are the first 5 people who raised their hands. Okay, so Harsha, Surya, and Shagun, I'm sorry, but there is a limit on the number of people I can nominate to be the President of the United States. I'm sorry, I mean class representative of S3 section. Yeah, and then these 5 people, you all can please cast your votes on Moodle, and accordingly that person will pick. Now, another thing is that I like to have some kind of social group. I prefer Telegram instead of WhatsApp. Telegram is much better in my opinion. So I will make a Telegram group, and I will share the invitation link with you all. Okay, so yeah, you
Yes, sir.
all can lower your hand now. I will share the invitation link, and you all can please join and share that invitation link in. So that group will be for the purpose of communication and
Sir,
class timing. हाँ जी बोलिए. You said, sir, I'm listening. But just now you're only walking around. Okay, never mind. I don't know what that was. Did you want to say something?
sir, I want to nominate for a CR.
Amrita, it's too late for that. 5 people already nominated themselves, and I can't allow an unlimited number of nominees. So first come, first serve, okay?
Okay, sir.
Okay, if of those 5, I find that none of them are acceptable, because ultimately this isn't really a democracy. We are just pretending that it's a democracy. It's like when you play doctor as a child, or when you play United Nations in high school. Think of like that. Okay. So now let me introduce you to the textbook that we will be using for this class and the course schedule. So I'm going to share my screen for that purpose. Okay. Second, course plan. Okay. Okay, fine. My desktop is here. Okay. So where is, so you can see my this course contents, right? This file here. I'm going to put that in the chat window also. Where's the chat window? This is the course plan. Then this is the textbook that I will be using for the course. Putting that also in the chat. So you can please download it and share a copy with your friends. Okay. So the course plan, let's see, etc., etc., etc. There are a lot of different choices for textbooks. I prefer number 3, which is Kenneth Crane, Modern Physics. I believe it's the best introduction. It includes almost all the topics that we want to cover. I personally, this is my own personal opinion and not the opinion of anybody else, is I think that this book, Asabaizer, is a terrible, terrible book and nobody should ever read it. So if Asabaizer is, or his descendants are watching this on YouTube, please don't take offense, but your book is horrible. And then, of course, you should all know that the internet is full of resources, right? So, for example, you have this thing called the MIT Open Courseware. Okay. Right, this is just one example. Then you have on YouTube, you go and there are literally hundreds of lectures on every topic, right? So I'll give you an example of this on YouTube. And this is the Moodle page. This is what the Moodle page looks like if you haven't already seen the Moodle page. And this is the live streaming of the YouTube on YouTube. Okay. So let me go to YouTube and show you what sort of okay. So for instance, if you want to learn about length contraction, okay, so you say length contraction, and see, you get lots and lots of videos. Now, if you see any video, like the first one, which says, for example, you can see BTech, BSc, MSc, Dr. Ashutosh Pandey, PhD Physics. That means you should
I can't.
avoid such videos.
I
Yes,
can't
Karan?
see a screen.
Well, can others see my screen?
Yes, sir.
Yes, sir. We
Yes,
can
sir.
see.
Yes,
Yes,
sir.
sir.
Yes, sir.
Yes, sir. We can see.
If anybody else is having trouble seeing this, my screen, can they raise their hand? So, Charan, I think you should you'll have to rejoin, leave the meeting and rejoin or something like
Sir,
that.
now
can't.
now I'm able to see.
Achha, good.
Yes, sir.
Okay.
So, can you please repeat what were you saying about this video, the first video?
Who is that? Sorry, it's hard for me to follow exactly who said that.
So, Nitin Kumar. So,
Nitin
I'm
Kumar.
asking. So, can you please repeat what you said about this length contraction video by
Okay. Sure. So, what I said was that when you see a video which has this kind of a screen, which is BTech, BSc, MSc, Dr. Ashutosh Pandey, PhD Physics, YouTube Technical Physics, that means you should avoid such videos. Okay, because most likely this is like a coaching class rather than somebody who is actually trying to teach you something. All right. Then of course you have these very nice videos by H.C. Verma. They're very famous, but you can see that the nature of our society is that H.C. Verma's videos has 1.4 thousand views, and Ashutosh Pandey's videos have 14,000 views. So that tells you the state of our society, right? Okay. Now there are let's see, very nice videos, animations. Let's just search for animation, because I believe that things which are visualized are learned better. Time dilation, length contraction. Okay, I can't find the one I'm thinking of. It's a person called Koronovsky. So let's look at this one, for example, length contraction and time dilation. Okay, so this is you can hear the YouTube audio?
No, sir. No, sir.
No, sir.
I
No,
think
sir.
I think
No.
because the audio is placed in computer and that's not shared. Right, there's no way to share that. Okay. Anyways, so you can if you don't understand what's going on in class, you can always look at such videos, so this has a nice animation here. It shows you gives you an illustration of length contraction as the view of a rod as seen by different moving observers. Okay, so here the resolution is not coming out very nice. Let me see if there's a better resolution. Quantity. Okay, no, 360 is the resolution. Okay, so I'm sure you can find better resources. Okay, let's close that. Okay, so now let me go back to the course plan. So this is the course plan, and now you will see in the course plan that we have 4 sections: special relativity, electromagnetism, then prerequisites for quantum mechanics, and then in the 4th section we have put mechanics, which is review of Newton's laws and related problems from Kleppner and Kollenkow. Now the thing is that most of you have already studied mechanics in great detail. And so many people find it boring if I discuss mechanics in the beginning. But there are many people who have also forgotten what mechanics is, and they have also forgotten the basic concepts like vectors and differentiation of vectors, integrals and all that. So what I will be doing in the next, over the next few classes is I will be going over this mechanics portion. All right. I'll take about four lectures for that. And then we will go to special relativity and ENM and so on. All right. Now let's see. So this is the general course plan, and you can see that there is some sort of a distribution of lectures. It may or may not go according to this, depending on how you all feel about each topic and how much I'm able to cover in each class. And this, by the way, here KK refers to Kenneth Crane, not to Kepler and Colin Cow. Okay, this is Kenneth Crane. Then this DG refers to David Griffiths, right? David Griffiths, Introduction to Electrodynamics. Right, and then this thing, the rest is all Kenneth Crane. Okay, any questions?
Sir, can you repeat which book we should follow, sir?
So for relativity and quantum mechanics, you should follow Kenneth Crane. And for electromagnetism, you should follow David Griffiths. Okay?
Okay, sir.
All right. And anything else?
Sir, is the syllabus reduced this year or is it the previous annual?
No, we actually increased it. We expanded it because, you know, we thought that you all have so much time at home, so you should be able to study more. So we have doubled the size from before. I hope that's okay with you.
Yes, sir.
Yes, sir. Yes, sir.
Okay, for those of you who do not have a sense of humor or cannot catch on to when I'm being, you know, sarcastic or silly, that was one example. Okay, so no, this syllabus is the same. We have kept the syllabus the same because the length of the semester for you all is basically unchanged. I think it's changed by a small amount, but you are supposed to have about 45 lectures or so. So there's no change. Okay. All right. Anything else? Okay. Right. I'll stop this sharing here, and then the way I cover the class contents is that I have this what do you call it? I have a tablet and with a pen, and I write on the pen on the tablet with this pen, right? So this is my blackboard, all right? So this will be my method, and PH1, PH110. Now let's see, according to your schedule, from 2 to 2:30. Okay, so I guess, and you don't seem to have any class after that. Okay. So today is December 15th, 2020. Just 1 second. Disturb 1 hour. All right. And I should also tell you my name and so on and so forth. So my name is Deepak. I'm in the physics department. I can be found in room 217. I've forgotten my own office number from so many days of not going there. Room 217 in the science block, which is not very relevant at the present time. Then I have an email address, tk.edu.in. So I request all of you to use this email address and this email address only for all course related communication. Okay, this is the official email address. Then, as you all have seen, I'm available on Zoom. Then I will also create a course group on Telegram, and so please join to share info, etc. And then the other resources that we have are Moodle. And then finally, I'm available on Zoom.
So where will you put the Telegram link?
Sorry?
Where will you put the Telegram link?
The Telegram link, I'll put it here right now, in fact. So let me do that. I'll take just 1 second. Telegram new group and people. And name 10, 3 December 2. Okay. One second, I'm trying to remind myself how I get the invitation link. Add members. Type. Okay, invite link. Got it. Invite link. Okay, that's the invitation link for the Telegram group. I hope you got it. I can see it in the chat. Okay. I can see many of you are already joining. Excellent. So please also share this link with all the people on your, you must have some class WhatsApp group and so on and so forth, right? I'm also available on Zoom whenever needed. Okay. So if you have any doubts and so on, you can message me. Please don't use WhatsApp for messaging if you can help it. And let's stick to one social media app. Also, you will obviously have access to my phone number, but again, please do not call me in the evening or early morning, unless it is for a life or death emergency. Okay, and this is a physics class and not a it's a physics class. There's going to be no life and death emergencies, presumably. So please don't call me. Be after 6 p.m. or before, let's say 9 a.m. Okay, or 8 a.m. Okay, so let's. Is there anything else? Right. And then as for assignments and so on, I will post your assignments on Zoom, on Moodle, and then you will also have. Through the course of the semester, you'll have 2 quizzes and 1 mid-sem and 1 end-sem. All right. And then for my other colleagues, my faculty colleagues who are covering PH110, the other section, many of them are going to make presentations, lectures, and recorded lectures, and you might be able to get those through your friends or contacts in the other sections, or maybe if I get them, I will share them with you. So you can also use those as a reference if you want.
Okay.
Okay. So now let's start with our discussion of mechanics. Okay. All of you are familiar. You have all studied mechanics, right? But let me remind you what mechanics is again. Mechanics is the study of the physical evolution, or I should say, okay, sorry about that. Of the structure,
Machines.
evolution of physical systems. Okay, now this is a very, very general definition, and as such it covers everything ranging from atoms to molecules to DNA to organisms and bacteria and even to human societies and ecosystems and so on and so forth, right? But of course, we are interested in a much more narrower definition, which is called classical mechanics, right? Classical mechanics refers to the study of the structure and evolution of, to be more precise, mechanical systems. Okay, so which are those amenable to a description by Newton's laws. All right. So what are the systems which are amenable to a description by Newton's laws? So if, for example, you have point particles, you can have a single point particle or many, and they can be either interacting, they can have forces between them, or they can be free. Then you can have rigid bodies. So rigid bodies means such as example, you can have spheres. Well, any solid rigid body, right? And then, or again, you can have one or more, and again the same thing, interacting or free, right? But we are mostly going to focus on this aspect, the point particle aspect, right? So in the usual setting of classical mechanics, how do we describe a point particle? We say that, well, first of all, what we do is we set up a coordinate system. And we say that, so our particles, or whichever are rigid bodies or whatever they are, they move around in space and they move around in time, right? So they move around in space-time. So how do we specify the trajectory of a particle? We say that a trajectory corresponds to a curve, right? in this. So this is the beginning, this is the end, right? I've just drawn some random trajectory. And mathematically, how do we express it? We say that the position of a particle is described by a vector x, which is a function of time. And then we define the velocity of the particle. Sahana cannot see the screen. Can others see my screen?
Yes, sir. Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
Yes, sir.
So again,
Yes.
Sahana,
Yes, sir.
please, you might have to log out and log in again. Somebody raised their hand, but they have lowered their hand, so I can't tell who that was. So the velocity of a particle, we define it to be the time derivative of the position, and this time derivative. Now I request all of you to, when after asking your question or saying something, I request you to mute yourself so that if there are any background noises, they do not interfere. So you take the usual definition of a derivative, which is that right? This is the definition of a derivative. It's just the limit of x, the vector x at t plus delta t minus the vector x at t divided by delta t, right? And so this vector again has three components. And if you want to think in terms of components, then we would write it like this: v of I v of I is equal to dxi by dt, where I in this symbol means in, right? So I is in the set x, y, z. Okay, so I will often be using notation of this form. I hope that you can follow it. If you are unfamiliar with these terms, you should mean in. Then there are some other symbols which means exist, something like this, means for all, which means therefore, which means because, and then we have something called QED, and
Quite
QED,
easily done.
that is not what it means. It means quad that demonstrandum. Of course, there is no reason to say that it only means this. It can mean this also. The original definition used to be in this way in Latin, which used to mean that. Which was to be proven. Yes, somebody wanted to say something. Is there anybody who were trying to say something? No? Okay. All right, so on and so forth. And then of course we have the usual symbol for the sum, right? Sum from, if I write something like this, what this means is x1 plus x2, so on till plus xn. I presume that you all know this, but I'm just mentioning this, just to make sure that nobody gets confused. Okay, so coming back to mechanics again. So this was a small detour to talk about notation. And if there are any other notational issues, I will bring them up later, okay? So coming back to mechanics, we define the position as a vector. We define the velocity also as a vector. And similarly, we can define the acceleration in exactly the same way. Acceleration is a of t, and this is dv by dt equal to d square x, vector x dt by dt square. Okay. So in terms of these quantities, we have the three laws of Newtonian mechanics, right? So Newton's laws. What are Newton's laws? Can you remind me?
Inertia of motion.
Action, reaction.
First one is inertia.
F is equal to ma second.
The second one is F is equal to ma.
Action is equal to reaction.
Third one is action. Okay, so these are the three laws of Newton, right? The first law says that basically it's more of an axiom that well, they are all axioms. I mean, you can't really you just have to sort of take them for granted. So the first one says that objects have some property called inertia, and inertia is what is a measure of how hard it is to change the state of motion of an object. So, and you know, the statement of the first law is normally that a system in some state of motion where continues to stay in that state of motion or in the state of rest unless acted upon by an external force, right? Which is basically that, you know, saying that if there is no external force, then whatever is happening keeps happening. The second statement relates the change in the system, which is measured in terms of an acceleration. And it relates that to an external force F. And it says that these two are proportional by a parameter called m, and this m is the mass of your system. So the greater the mass, so what you have here is that the acceleration of a system is equal to F by m. So that means the greater your mass, the less responsive your system is to change, right? The greater your mass, for the same value of the force, you will have a smaller acceleration. And what is acceleration? Acceleration is a measure of the change in velocity, right? So you have some particle, it is, if it is left alone, it is moving with some velocity. What will happen? It will keep moving at the same velocity forever and ever, right? That is the statement of the first law. So if you apply an external force, what happens? You change the state of the motion. How do you change the state of the motion? You change it by some amount delta V, right? And when you change it, then your particle starts moving in a different direction, let's say, right? So this is what we mean by change in the state of motion, right? And unless and until there is an external force, there is no change. And if there is an external force, then the change is depends on the inertia of the system. If this m is large, this delta V will be small, otherwise delta V will be large. And then we have this law of external of action and reaction, which says that if you have two systems which exert forces on each other, so for example, you can imagine that you have two people and they are pushing against each other, right? But they're also standing on the ground. So we'll call this system 1, call this system 2. So the force that the first system exerts on the other second one is F12, and likewise F21. So what this says is that F12 is equal to F21, right? But also these people or objects or systems, they're standing on the ground. So for instance, you can say that there is a force with which this person is pushing the ground. So you can call that F2G, but then there will be a corresponding force with which the ground is also pushing the person back. That is FG2, right? Because when you go like this, you have to push backwards. But then there is also the force of gravity, which is pulling the person down. So this is, I'll call this this is one force. Then there is F2 grav, and then F grav 2. Okay, so to speak, the vertical force with the force of gravity. Right? Now there is a problem with this law in particular, which is that it assumes that forces can be transmitted instantaneously between systems. All right. So, for instance, if I have two particles which are at separated by some large distance, let's say 1 light year. Okay, then Newton's law says again that F12, right, is equal to F21 according to Newton. But but this requires, so if this is true, then we require an infinite speed of propagation for physical influences, right? For physical influences, which means that for any force that is transmitted between systems or any communication between any two systems, there has to be an infinite speed of propagation, right? Otherwise, if it is not infinite, then what you will find is that F12 is equal to F21. So also I should be careful, there should be a minus sign here. F2 minus F21 minus sign here. Somebody is asking if the recording of the class will be available, and yes, the recording will be available. The class is being live streamed on YouTube, and that will be available for you to watch later. If for any reason I am not able to live stream it, I do record this class on my computer and I upload the recording on YouTube. So if you miss some portion, you will be able to watch it later on. Okay. So we have F12 is equal to F21, not at the time t, but at some earlier time delta t. No, I don't upload it on Moodle because on Moodle you cannot upload large files. So this will be at some time delta t, which measures the amount of time it takes. So now you imagine that you have, this is the time, and then this is space, or separation or distance or whatever. So this is t and this is x. So this is the system 1 at a time t1 and a system 2 at a time t1. And then you have, or I'll just say at a time t. And then you have the system 1 at a time t plus delta t and the system 2 at a time t plus delta t, right? So if you say that information cannot propagate at an infinite speed, then what happens is that if there is some change in the system at time t, then this influence will propagate at some velocity, right? And it will affect the system at time t plus delta t. And similarly, if same thing for the other direction. Okay. Finite speed of propagation of information or slash signal. All right.
Sir,
Yeah.
will you please repeat that? Why the delta t taken there? I can't understand.
Well, delta t measures the amount of time it takes for the signal to travel from point from system 1 to system 2, right?
Yes, sir.
So
So it is applicable only in when distance between the particle is large.
well, large compared to the typical velocities of your signal. Okay. So, for
Yes,
instance, we will see in relativity, right, that the rate of propagation of information is limited by the speed of light, c. So we can also take c to be, for example, the rate at which the gravitational force between two particles is transmitted. So
okay.
if two particles are close by, such that it depends on what you're asking, right? So if you're saying that I'm looking at the changes of the system on some time scale, okay? Let's say I want to measure the changes in my particle's position on a time scale of one second. Okay, I want to know what the particle does every second. That is my resolution, right?
Yes. Yes.
Then how far can light travel in 1 second? Delta t into 3 times 10 to the 8. It can travel 3 times 10 to the 8 meters. All right.
Yes, sir.
So as long as you consider the particles which are within this distance, right? You will be able to follow the motion of the particle from 1 second to the next.
Okay.
Okay. Right.
Yes.
So it depends on the question that you ask. Similarly, if I ask the same question for a different time scale, let's say 1 year, then of course this distance will be much more different, right? But
Yes, sir.
this ultimate scale is set by the speed of light, right? Okay. So now, right. So this is something that we will see is actually the situation in relativity. And so in relativity, Newton's law of action and reaction is no longer valid in the same way. Okay. So this is the concept of acceleration and velocity. Then we define another property, another quantity, which is called the momentum. So the momentum is defined as the mass of a object times multiplied by its velocity, right? And the correct statement of Newton's second law, which you normally see as F is equal to ma, this is not exactly the correct statement. Correct statement is that the force is equal to the rate of change of the momentum. So if I look at this quantity, the momentum, and I take the time derivative of the momentum, what do I get? I get m times dv dt plus dm by dt times v, right? Now this part is ma, but this part is extra, right? This part is there only if your system has a time dependent mass, right? Now, normally we don't really talk about such systems, but there are many such systems in nature, right? So one example is rockets or airplanes or meteors, right? So there are many examples of systems which have a time dependent mass. So as a rocket travels, it releases fuel, right? Fuel is burnt up and released, and the thrust is generated by the burning of that fuel. So the mass of the rocket keeps decreasing with time, right? So in that case, you have to include this term, right? Now, so what this tells us, that let's say that the external force on a system is 0, then the corollary is that dp by dt is 0, which means that p is conserved, right? So that means the momentum at a certain time t is going to be equal to the momentum at a later time t plus delta t, right? So the momentum of a system, of an isolated system which is not affected by any external force, does not undergo any change, right? Now this is fine, but it's not very useful. For a single particle, it's not useful. It becomes useful when we consider composite systems. So a composite system means, for example, two particles, right? Again, the particles can be free or they can be interacting. We don't know, it doesn't matter. So we will label those particles, their positions by 1 and 2 respectively, x1 and x2, right? And we can write down the velocities and also the momenta for the two particles in the usual way, right? Now, what we can do is we can define a total momentum. A total momentum can be defined for the system, which is the sum of these two momenta, right? And this is where vector algebra starts to come into play, right? So if you have two particles, one particle has momentum p1, the second particle has momentum p2, then what is the momentum of both of the entire system? Well, you take the vector sum of these, and so this is p1 plus p2, right? In terms of components, the x component, and so this is the component wise sum, okay? You all probably know that, but in case you don't, I'm just reminding you. And now we have Newton's law, which says that F net, the total force on the system of two particles, is given by this expression. So if there is no external force, the net total force from outside is 0, then what this tells us is that this is 0, And what that tells us is that dp1 by dt plus dp2 by dt is 0. Right? Now, what is the meaning of this statement? The meaning of this statement is that at any instant of time, the sum of the two momenta, P1 plus P2, is equal to a constant. If the external force is 0. Right? So we can use this to solve problems. So for example, if you think about it in one dimension, if you think for simplicity in a 1D problem, so an example of a 1D problem is, let's say you have a particle here that is moving with some momentum P1 and another particle which is moving with some momentum P2. Then these two particles come together and they collide. After the collision, you find that particle 1 is moving with some momentum P1 prime and particle 2 is moving with some momentum P2 prime. Right? And I've not put a vector index because we are only in one dimension. In one dimension, there is only one component, right? But I will put a vector index so that you remember what is going on. So what we know now, right, is that there is no external force on the system. So what we have is that P1 plus P2 will be equal to P1 prime plus P2 prime. This is the statement of conservation of momentum, right? Okay. Now by itself, this is not enough. We need another, because let's say that you are given the initial momenta of both the particles. You cannot use this one equation to solve for the final momenta of the particles because you have two unknowns. You have P1 and prime and P2 prime. These are your unknown quantities. So you need two equations, right? So the second equation that you can use comes from conservation of energy, right? So we have Pn square by 2 m1, P2 square by 2 m2, right? P1 square by 2 m1, P2 prime squared by 2 m2. And what is this delta E? So let's say there is some energy lost in the collision process or gained in the collision process without any change in the mass for simplicity. Then for instance, this measures this is the inelastic part, right? So if delta E is 0, then your collision is elastic. No, I'm sorry. The elastic is if there is no extra delta P here. So if momentum is conserved, your collision is elastic. So, okay. So this is your inelastic part. Energy, total energy is always conserved. Okay. So with these two equations, you can solve for P1 prime and P2 prime. And this is conservation of energy. All right. Now, where does this concept of energy come from? I will talk about in the next class. Okay. I think we have had enough for one day. So I will leave it here and we'll talk about how to define energy, why energy takes this form of this quadratic form in terms of the momentum. We'll talk about it tomorrow. Okay.
Okay.
Now I can see that about 20 8 people have joined the Telegram group. So yeah, so please, I request more of you to join. Okay. All right. Any questions for now? Okay. So we will meet again. Today is Tuesday. We'll meet again tomorrow, and tomorrow we'll meet at 11 a.m. Okay.
Yes, sir. Oh, okay, sir.
Okay,
Thank
sir.
you, sir.
Oh,
Thank you,
all
sir.
right.
Thank you, sir.
Thank you, sir.
sir.
Thank you,
Thank you,
sir.
sir.
Thank you, sir.
Thank you.
Thank you,
Thank you,
sir.
sir.
Okay. All right. So I'm going to end the session.